This is part 2 of the video notes for Objective 10 vectors. These video notes correspond to sections 5.4 and 5.5 in your textbook. In the last section, we went over the ways to notate a vector. We have component form, we have a linear combination, where I and J are bold, and we have a magnitude and a direction. So in this portion of the video notes, we're going to talk about the different operations that can be completed with vectors. So if you consider a vector A to have components A1 and A2, and a vector B to have components B1 and B2, we need to define all of our standard operations. And the standard operations are addition, subtraction, and multiplication. So we're going to start with addition. To add the vectors, you just need to add their component forms. Similarly, if you'd like to subtract the vectors, you just need to subtract their component forms. So I'm going to go ahead and make these a plus or minus, since addition and subtraction work in the same way. Now, scalar multiplication and standard multiplication, which we call a dot product in vector form, is different. So we need to talk about what a scalar is. If a vector is a quantity that has both magnitude and direction, so think of a vector as velocity, or force, or acceleration. These are all things that have a magnitude and a direction. For example, velocity has speed, force has force measured in newtons, and acceleration has, well, acceleration measured in meters per second squared or some other set of units. The scalar quantities are those that can be measured with a single quantity and no direction. Think temperature, distance, speed, which is velocity without direction, and time. So a scalar is more like a magnitude and no direction. Well, that means we need to define one type of multiplication as scalar multiplication. What does it mean to take a distance or a speed and multiply it to a vector? So in this example, we'll let k represent our scalar. K is not bold. And to multiply a scalar to a vector, you just need to distribute it to both of the components. So ka1 and ka2. So think of scalar multiplication like the distributive property. The last type of multiplication we need to define is the dot product. And so the dot product is notated with a dot. And to find the dot product, you need to take the horizontal components, or the product of the horizontal components, and add it to the product of the vertical components. Now, it's important to note that the sum or difference of two vectors is a vector. The scalar multiplication, so scalar times a vector, is a vector. But the dot product of two vectors is simply a magnitude. This does not have a direction. This is not a vector in component form. This just gives you the magnitude of the two vectors multiplied together. So let's try each of these operations. So I'm going to give you two vectors. We're going to let u be the first vector, and the component form of u is -1, -3. And then we're going to let v be our second vector, and its component form is 3, -4. So we're going to find u plus 3v, which will allow us to practice scalar multiplication as well as a sum. And then we're going to find the dot product of u and v, which again is not going to be a vector, but a singular value, a scalar value. So let's do u plus 3v. -1 minus 3 plus 3 times 3, -4. So again, scalar multiplication is distributive. -1, -3, plus 9, -12. And then we add them together, 8, -15. As you're working through these problems, say on an assessment or on practice, how much of the scratch work should you show? It's important that I can see what your process is, but maybe you don't do it in 2 steps. Maybe you do a singular step and show the double application of addition and scalar multiplication by writing -1 plus 3, comma, -3 plus 3, -4. This combining of the steps can get confusing. You may forget what to put in each piece. I prefer to separate out my steps, show each equality statement along the way, but this would be an acceptable way to show that you understand the combination you're completing. Now let's do the dot product. The dot product is defined as A1 times B1, which in this case we'll call UX times VX, plus UY times VY. So we're going to take -1 times 3 plus -3 times -4, which gives us a magnitude of 9. So the dot product of U and V is the scalar value 9. The last operation that we need to do with vectors, and we're going to go ahead and do it on our same U and V vector, is to find the angle between the two. Again, this is more of the trig side of vectors. So to do this, you can simply apply the formula. The formula for the angle between vectors is cosine alpha equals the dot product divided by the product of the magnitudes. So again, remember that cosine, sine, and tangent are all just ratios. And so the ratio we're looking at is the product of the vectors over the product of their magnitudes. Let's apply this formula to our specific vectors. But before we do that, I just want to get an image so I can get a feel for what I expect the answer to be. -1, -3. And in this case, I'm trying to make my scale pretty accurate. This is U. And 3, -4. This is V. Now that I have a visual, I know what kind of answers would make sense for the angle in between the vectors, and I can apply the formula. Cosine alpha equals the dot product of the vectors, which we found in the last example to be 9, divided by the product of their magnitudes. So I need to find the magnitude of each vector. Let's start with the magnitude of U. The magnitude of U is equal to the square root of -1 squared plus -3 squared, which simplifies to be the square root of 10. The magnitude of V is the square root of 3 squared plus -4 squared, which simplifies to be the square root of 25, or 5. This is a 3, 4, 5 triangle. And so we would have the magnitude of U times the magnitude of V. I don't have to rationalize this answer because I am actually just trying to solve for the angle. So I'm going to go ahead and apply my inverse function and say alpha is equal to inverse cosine of 9 over 5 radical 10, and use my calculator in degree mode. And so I get that alpha is approximately 55 degrees. Cross-check that with my graph. Would it make sense for this angle to be 55 degrees? Yes, it would. And these are all of the operations that I need to be familiar with when completing operations with vectors. This concludes part 2 of the video notes for Objective 10, vectors. In the next part, we'll see how vectors relate to application problems using force, velocity, and acceleration, and how these operations look in context of a real-world problem.